Now let us take a specific example. N2 plus 3H2 gives rise to 2NH3. Now, see in this case, rate of disappearance of nitrogen can be given as minus the concentration of N2 by dt, right? Similarly, rate of disappearance of hydrogen can be given as minus a dH2 by dt. And then the rate of appearance of ammonia can be given as plus d concentration of ammonia by dt. See here, there is an important thing. Do not consider the number of moles while writing the rates of disappearance and appearance. Right? Very important. I'll tell you why after this. Now, rate of reaction in terms of N2, H2 and ammonia can be given as, right, minus the concentration of N2 by dt, that is equal to minus 1 by 3 d concentration of H2 by dt, that is equal to plus 1 by 2 d concentration of ammonia by dt. Now let us check all the things. Supposing if you consider the rate of appearance of ammonia and the rate of disappearance of nitrogen. Take this two here. It can be said that the rate of appearance of ammonia is at 2 times the rate of disappearance of nitrogen. Twice of the disappearance of nitrogen, because 1 mole of nitrogen is disappearing and 2 moles of ammonia is what you are getting. Is that okay? Then, considering the ammonia and hydrogen thing, look at this. So this is the rate of disappearance of hydrogen. The thing rounded off. Come on, take it here. Now, the rate of appearance of ammonia, the thing rounded off only, is equal to 2/3 of the rate of disappearance of hydrogen. Hope you got my point. 2/3 of the rate of disappearance of hydrogen. 2/3 of 3 is 2. Now, even if you want a relation between these two, this and this, come on. Rate of disappearance of hydrogen is 3 times the rate of disappearance of nitrogen, isn't it? Now, see, I told you not to consider the number of moles. Let us suppose if you consider number of moles, even while writing the rate of disappearance and appearance, then suppose if you consider 1 by 3 here, it will become 1 by 3 into 1 by 3, 1 by 9 times. Think you got my point? So never ever consider number of moles while writing the disappearance and appearance. You can take them, of course, while writing the rate of the reaction. Okay, check this out. Now, let us go for the next topic, that is factors affecting rate of reaction. See, there are several factors which affect the rate of reaction. Let us start with the nature of reactants. Yes, the nature of reactants affects the rate of reaction because the reactants can be of two types. They can be ionic, they can be covalent. Okay. Now the reactions that take place between ionic compounds are called ionic reactions. You know, these are fast, or we can say instantaneous. Just like the example what we have taken in fast reactions case. Look at this. When aqueous sodium chloride is added to aqueous silver nitrate, a precipitate of silver chloride is formed within 10 power minus 4 seconds. This is a reaction. And if you consider the ionic equation of the same reaction, what? See, it will be Ag plus NO3 minus plus Na plus then Cl minus. Now, the thing that actually happens during this is exchange of ions. You can also say grouping of the oppositely charged ions, as a result of which you get a precipitate of silver chloride, whereas the Na plus and the NO3 minus remain as such. You know, these Na plus and NO3 minus are called spectator ions because they have got no chemical change. They have undergone no chemical change during the course of the reaction. Now then, what is the net equation? Therefore, net equation is Ag plus Cl minus gives rise to AgCl precipitate. Removing the spectator ions, the final equation can be written this way. It is nothing but exchange of ions or you can say grouping of the oppositely charged ions. Yes, they have exchanged their ions. Now coming to covalent compounds, you know the reactions that take place between covalent compounds are called molecular reactions. These are slow. Let me give you an example. The combustion of methane. See, in this reaction, you know, it occurs slowly because you need to break the bonds between reactants, I mean, between atoms of the reactants. And then you need to form bonds between the atoms of the products. You got two different things. Cleavage of the bonds, formation of the bonds. Bond breaking and bond making. This and all, in fact, requires energy, of course, time. So these are slow. But even within this also, we can give something interesting. If suppose you got two reactions, one involving the cleavage and formation of less number of bonds, the other one involving the cleavage and formation of more number of bonds, the one that is involving the cleavage and formation of less number of bonds occurs quickly compared to the other. Isn't it? Look at this. Within this, fast if involves cleavage and formation of lesser number of bonds. than the one with more number of bonds. Look at this. So this is all about the effect of nature of reactants on the rate of reaction. Now, let me take the second factor that influences rate of reaction. That is concentration of the reactant. This, of course, can be given based on law of mass action. We know that according to law of mass action, rate of a reaction is directly proportional to the product of active masses of reactant. What do you mean by active mass? This is nothing but molar concentration, nothing but molarity, represented by writing the symbol or formula in square brackets. So anyway, rate of the reaction is directly proportional to concentration. So for a reaction, A plus B gives rise to products. If the rate expression is written, it can be written as a rate is equal to K into concentration of A into concentration of B, isn't it? Or else it can be written as rate is proportional to the product of active masses of the reactant. Then go for rate is equal to K into concentration of A into concentration of B, where this K refers to rate constant or specific rate. Okay. Let me give you an example. Supposing if you consider the reaction between zinc and concentrated HCl and a reaction between zinc and dilute HCl. You know the reaction that occurs between zinc and concentrated HCl takes place quickly. This is fast, this is slow. It can in fact be explained on the basis of collision theory of reaction rates, about which we will be discussing later. But for now, remember, the concentrated HCl will have more number of molecules per unit volume. So you'll have more number of collisions taking place. Whereas dilute HCl will be having less number of molecules per unit volume. So the number of collisions will be less. So this can be explained on the basis of collision theory. But overall, as the concentration of the reactant increases, rate of reaction increases. Okay.